Okay, hello and welcome to Algorithms Live. This week I'll be talking to Mikhail Tikhomirov. And so let's learn a little bit about Mikhail. So you'll know him from his top coder handle, Endagorion. He's the coach for Moscow Institute of Physics and Technology. So they've gotten 2 gold medals and 1 silver medal in the last few years under his coaching. He was a finalist in TCO in 2014 and 15 and Google CodeJam in 2017. He's authored many problems on various sources in Russian contests and Codeforces. And he was also a coach of the Barcelona bootcamp, which some of you may have seen posts on for Codeforces. So Mikhail, thanks for coming on Algorithms Live.
Yeah, thanks for having me.
All right. First question I wanted to ask you is, do you have a story about your Codeforces and Topcoder handle?
I don't know. The handle is very old, so I don't exactly remember how it came to be. But I guess it has to do with some I used to be obsessed with the Lord of the Rings stuff, fantasy, and that sort. So it's probably some sort of Elvish name, maybe.
Okay.
I'm not sure.
Pretty cool. And so the problem we're talking about today is this Altol's caves problem. And you wrote this for the Barcelona bootcamp, correct?
Yeah, we have in the Barcelona bootcamps, we usually have a special Codeforces round. So this was the last problem from, it was actually autumn of 2017, I checked. So yeah, it was the hardest problem. I don't think anybody solved it during the competition. It's reasonably hard.
Okay. So, yeah. And so what's the story behind the name or the Altol caves?
Well, the problem is about searching for treasure in some sort of environment, and Altol caves is a system of caves near Barcelona. So I thought it would be nice to link to Barcelona somehow.
Really cool. So I guess we can switch to your display so we can start talking about the problem.
Let me turn on the screen share real quick. Okay, now we're good.
Okay, so I've switched over to you, so we should be good.
Mm-hmm. Okay, do you see my screen now?
Yep. And it shows up on the broadcast too, so we're good.
Okay. Right. So let's talk about this problem, about the setting first. So we have these end spots. We'll number them from 0 to n-1. It's going to be convenient later. So one of these spots, they were caves in the problem. So one of them contains the treasure, and we don't know which one. It's actually random. The probability of each cave containing the treasure is 1 over n, so it's equiprobable. And so we're starting searching here, and what we can do in one day is to select a bunch of caves we want to search, and we search them kind of simultaneously. The number of caves we can search on each day. Okay. So we can search at most k caves each day, and we want to search as much as possible. So, but the trick is, so if none of these caves contain the treasure, then naturally we just don't find anything. However, if we do search a cave with treasure, then it's still 50-50 chance that we find it, because we could miss it, or I don't know. Right. So yeah, and we want to find the treasure as fast as possible on average. So we want to choose a strategy for searching the caves on different days, so that to minimize the expected number of days until we finally find the treasure. Okay.
Mm-hmm.
Right. So the limitations for this problem were quite large. It was n up to 500 million. I think it's a kind of special number. In fact, I'll probably talk about this later. And the answer we should output, you can sometimes see in the problems, if the answer is like p over q, so it's actually always a rational number. So if it's p over q, then we want to output p times the inverse of q modulo 10 to the 9 plus 7.
And it's the reduced fraction of p and q?
Yeah, it's supposed to be reduced. So in order for this to exist, q has to be not divisible by this modulo. And it's like in these limitations, this is always the case. In fact, so yeah, well, when you see these kinds of like when you're supposed to output the number in that form, what you usually do is you just do all your arithmetics modulo this number, right? So when you want to add numbers or subtract numbers, you just do that modulo something. You can also multiply numbers, modulo the same number. So like each of these are like, if we were to compute it precisely, it would be a rational fraction, but doing this kind of preserves this value modulo the prime number. We can also divide numbers, provided that y is not 0 modulo p, modulo this number. So yeah, to divide something, you want to compute the inverses, and this is due to small Fermat theorem is just y to the p minus t. So you use fast exponentiation here, and you can use that to divide something. So if these are the only operations you're using, then basically what you're doing is like you're doing the same operations you would do for solving the problem, like in any kind of numbers, in doubles, for example. But instead, you do like all of these modulo prime number, and that's basically the only difference. So I'm not going to focus too much on the answer being a modulo prime number, because that's not very different. Okay. So the statement is like kind of concise, right? It's pretty clear, like how the process happens here, but it's still not quite obvious. Well, first of all, like what should be the strategy, right? And second, even if we know the strategy, how to compute expectation. So yeah, let's talk about that probably. So so let's say that like x is this random variable that's the number of days until we find the treasure. So we want to compute the expected value, right? So the usual formula for that is like this infinite sum k times the probability of x being equal to k. That's the definition of expectation, right? But we kind of want another kind of formula because like we can think about x as, we can say that x is the sum of x1 and x2 and x3, this infinite sum of random variables, where xi is equal to 1 if we're still not finished on day I, and 0 otherwise. Yeah, and so x is like naturally the sum of all of these, right?
Yeah, so this is the linearity of expectations formula, just doing transform.
Well, yeah, we just wrote x as the sum of these, the sum of all these like indicator variables, but now we can apply the linearity of expectation to that. So instead of this like explicit definition, we may write, let's say, like, so we can say EXI, right? And this is the probability that we are still not finished on day I, right? Because the expectation of that is just the probability of this happening.
Mm-hmm.
And right. So, and yeah, we will kind of need that at the end. And we can also write that as the sum, like our treasure is if we probably distributed here,
Mm-hmm.
right? So we can say that it's the sum of expectation of x, provided that the treasure is at the spot j. Okay, that's like the law of total expectation, I think. And then we should also multiply by probability that this actually happens, that the treasure is at j. But this is 1 over n.
Mm-hmm.
Okay. So here, this is like slightly simpler to think about it, because like we know where the treasure is, and so the only randomness left is when we search for the treasure at j, do we actually find it? Because that probability is like 1/2 each time. So we can look at it like that. So let's look at the spot j. Right? So our strategy is actually, when we choose it, it does not depend on anything, because we choose in which order we search these caves on each day, and then we kind of keep searching until we actually find the treasure. There is no like adaptability or anything. So for a treasure j and our supposed strategy, whatever it might be, let's look at these days from 1 to infinity. And so for each day, we will know whether the cave j will be searched or not. So for example, on day 1 it was searched, on day 3 it was searched, and I'm sorry, on day 2 we missed it, and so we have this sequence, right, of on which day do we actually search this cave. So how do we compute these based on this sequence? We may actually like use kind of the same idea. We want to sum the probabilities of not finishing on day 1, 2, 3, and so on. Okay, so what the probability we did not finish on day 1? Well, it's 1, because well we cannot finish when we still didn't search anything, right? So day 1 will have to happen. But then as we search, right, with probability 1/2, it's over, but with probability 1/2, we still keep searching. So the probability of surviving to the next day is 1/2. Okay, if the treasure is actually here. If we do not search the cave, then the probability doesn't change, because whenever we survive here, then we survive here. And then as we search for the next day, it's going to be 1/4, and so on. So based on this sequence of like searches and not searches, we can write down this sequence of numbers, okay, which have the same meaning as this xi, just applied to the case when we only have like one cave. Okay, and so this number is actually equal to the sum of all these numbers. Right? So that at least gives us some idea about how can we compute the expectation if we know the strategy, right? Okay. So so now what's the optimal strategy? And yeah, let's look like at the picture as a whole. So we have this for this j, we have only one sequence of numbers. But if j is, like, if we consider all possible values of j, so we search some caves on each day, like here. So this is day 1, for example. This is day 2. We search some other caves, and so on. So for each j, we can compute all these numbers. And so on. Right, it's 1, 1. Right, so we have this table of numbers, and the answer, as you can see from this formula, is actually the sum of all these numbers in this infinite table multiplied by 1 over n. Right. So we so what's like the natural it should be 1/2. So it's natural to expect that since we want to minimize the sum of all the numbers in the table, we want to make our searches so that to make like to decrease the largest number, right? So that corresponds to the fact that like we don't want to be too focused on any particular cave. In our searches, we want to kind of separate the searches evenly, which kind of makes sense because it's symmetrical, right? Any cave has equal probability of containing the treasure. So we can think of this as a greedy algorithm, right? So let's say that our strategy is to, on each day, search k caves, like that we've searched for the least number of times before. Yes, less frequent caves, right? So that's going to be our strategy. Right. How one can actually prove that this strategy is optimal? Well, we can look at this table and kind of see. We want to give a lower bound on the answer, and we're going to give it in terms of the sum in these columns over here. So, like after, let's see, after I days, the total number of searches that we've made with multiplicities, right? So we had made total of I times k searches. And so let's say that we've searched the cave 0 a0 times, cave 1 a1 times, and so on. So the sum in this column is going to be sum over minus 1. Sum over j from 0 to n minus 1 to the power of minus aj, right? So if we didn't search the cave, then it's still 1 in this table. If we search 1 time, that is 1 in 1/2. If 2, then it's 1/4, and so on. And yeah, since we've made the total of I times k searches, then the sum of aj is I times k, right? So what's the smallest value this can have? So in fact, we can prove that this is minimal when aj are as close as possible. So when all differences between aj are most 1. Because if we could, otherwise we could rebalance the searches so that this sum is smaller, right? So if we had a cave that searched 0 times and another cave that was searched 2 times, then that would give us basically 1 plus 1/4. But we could rebalance it to search each cave only 1 time, and that would give us 1/2 plus 1/2, which is better.
Yeah. So basically the idea is you're taking this very general strategy that anything could use and comparing it to your strategy and just showing that your strategy is always at least as good as anything else you can do.
Yeah, exactly. So so here, when we are only bounding the number of searches of the caves as a total, it may not correspond to any actual strategy, right? Because with these rebalancings, we could retroactively not search a cave, so that's not a thing. However, even if we allow this, the answer we produce for this generalized strategy cannot be better than the answer for our actual strategy. And in fact, when we do that, this is exactly what happens, right? Because when we do this, the differences in frequencies are never larger than 1. So one particular implementation of that would be right. So again, we have caves like these. So first we search for the first k caves, then for the next k caves, until we run out of caves. In which case we search for all the remaining ones that were still not searched, and the remaining, the rest ones that are not used here, are going to be the first few caves, right? Because it's kind of indifferent now. They are all equally searched at this point.
Yeah, I actually drew out an example, so I can switch to mine real quick and then just show.
Oh, okay.
Yeah,
sure.
So here's the layout. I'm transposed from Mikhail's example here, but here's the idea. So I have days down here. So I'm moving down in days, and these are the cave spots. So there's 7 caves and then infinite number of days. And you can see I'm searching 1 through 2, so like this. And then it moves to the next cycle, 3 through 5. And then it moves to 6, 0, and 1. So you can see just the blue marks where I end up moving. And you can see how the probabilities change. So it starts, everything is equal probable. And then you have a few 1/2s in the beginning over here. and then the remaining piece is all probabilities of 1, and it just continues like this infinitely. All right, so let's switch back to yours, I think.
Yeah, okay. Right. So, okay. So, in fact, so the strategy is fixed now, right? We don't have to think about that anymore. So how do we, so we are kind of approaching the solution. So let's think about like at least some way we can compute the answer in like without thinking about the constraints. So yeah, one more observation actually. So with this strategy, we're searching in these blocks of K, right? So if we say, for example, then that n is 6 and k is 4, then we're going to search from 0 to 3. Then we're going to search like 4, 5, 0, 1. Then we're going to search 2, 3, 5, 4. And then it's going to be looped again. So what you can see is we can separate all the caves into these blocks of 2, and these are always searched together, right? That is because both n and k are even. So yeah, that means that we always search these blocks together. And so what that means, like, is we can kind of think of each of these blocks as one separate cave, and we can divide both n and k. Right, we can divide both n and k by the GCD of n and k. So without changing the answer, because
so
that would
merging cave 0 and 1 to be one cave 2 and 3 to be one cave 4 and 5 to be one cave.
Yeah, so this is going to be new cave 0, this is going to be new cave 1, this is going to be new cave 2, and it's still equiprobable between them, right? It's still random. So doing this does not change the answer, and it's going to be a bit simpler after that. Okay, so like so we now have a very different, a very definite pattern how to compute the numbers in this table. We start with ones, then we divide something in half, then we divide like these tables, like in the picture Matt just showed you, right? So, but we cannot compute the sum for an infinite table, right? Because it goes on and on and on. Mm-hmm. However, we can see that after n days, so at day n plus 1, our searching strategy kind of loops around, right? Because we're like moving forward model, we are kind of, so if we look at these spots, like where the interval starts, it moves forward k modulo n, right? Mm-hmm. So what that means is that after n days, we're going to come around, and the searching kind of loops again.
Yeah, let's switch back to my example, and I can show exactly where that occurs.
Yeah, sure.
So you can see that in this example, n equals 7 and k equals 3. And so this is day 1, and you can see we're sampling at the beginning of the distribution. If I go all the way out to day 8, so this is n plus 1, we get back to the same starting case, and you'll see that this looping matches back up.
Mm-hmm.
Okay.
Yeah,
so,
and can we actually stay on your screen for a while?
Okay, cool.
So yeah, what you can further notice is that on day 8, all the probabilities are equal, right? All of them are 1A. Mm-hmm. Right. And so what that means is, still, since the searching is the same as well, then the numbers for day 9 are going to be like 8 times smaller than day 2, right? Because the same numbers like get multiplied by 1/2.
So
And
you
that,
just divide by or multiply by 1/8 this table to this table, right?
yes, exactly. And it's going to be the case for all the subsequent days, right? So we can think of that as like taking the square of first 7 rows.
Okay. So up to here.
Yeah, and then kind of repeating it indefinitely, but just multiplying it by 1/8 each time.
1/8. Yeah, mine doesn't go much further, but you could jump down here, also multiply by 1/8. Okay.
Yeah, so and now we can kind of compute the sum of all those numbers, because the first square is finite, so we can compute the sum in it like explicitly and say that it's like S, right?
So S is sum of all cells.
Yes, and the actual sum of all cells in the infinite table is going to be S plus S over 8 plus S over 8 squared, and so on, right? So like we could use the formula here for the geometric progression. So it's going to be S plus this geometric progression with multiplier 1/8.
Okay, so do something like this to infinity, and then S over. So that's I'll use n because it's n from the problem, or n plus 1, right? So
I think it's actually 2 to the power of k. So this 8 is 2 to the power of k, because that's the number of times we would search in each cave within a period. Okay, so it's going to be 2 to the I times k. Right?
2 to the I times k like this, or
No,
k
on
and
top. Yes.
Okay.
Yeah, and now we can sum these as a geometric progression because we have a closed formula.
And so what's the closed formula for this?
It's going to be S over 1 minus 2 to the minus k.
This?
Yeah, exactly. Right. Great. So now we have at least some algorithm for solving this, right? Without having to computing an infinite number of things. And so the only thing we have to compute is S, and we can do that in like n squared times if we actually compute the table, or in nk time, because only k numbers are changing on each step.
Yeah. That makes sense. So you can, it's kind of like dynamic programming, but you're sparse.
Yeah, we're just multiplying some numbers by 1/2 and keeping track of the sum.
Okay.
Not the
Yeah, so maybe not dynamic programming, but yeah. And so
yeah, let's go back.
Yeah. And then, but this is too slow because you set n to be 5 times 10 to the 8.
Yeah, and n is very long.
Hello?
K could be optimal for this
I
problem.
lost audio for you for a bit.
Sorry?
Oh, I lost audio for you for a bit.
Is the Kenya?
It's back now, yeah.
Great. Yeah, and what I also did mention is like n is large, but we also have 1,000 test cases to solve.
Oh, yes. So
So
T is up to
that
1,000. So
yeah, there is no chance of solving it with this approach. But right. So now let's talk about this thing. Okay. So this was remember for a day J, we would write down this pattern, how are we searching, and then we would sum up all these numbers. So now we're going to make observations. So let's say that xj is the expectation of x, provided that treasure is at spot j. Okay. So, like for example, let's look at I don't know, n equals 8 and k equals 3, and let's look at j equals 0 and j equals 3. So they differ by 3 by k. So can we establish a relation between how we're searching this case? So okay, on day 1, this cave will not be searched, right? Because it's not in the first k caves. So it's not going to be searched, and this is actually going to be searched. And on day 2, this is going to be searched, and this is not, and so on. So what we can actually tell about these sequences is that, like, when we searched here on day 1, right, then it's kind of clear that we would search these on day 2 because we always move forward by k, right, modulo n. Remember how we always move our segment by k modulo n, right? So that means is whenever we search 0 on any particular day I, then we're going to search 3 on day I plus 1. Okay, because if a segment on day I covers 0, then we're moving it forward by k, and it's going to cover 3, regardless of what the segment actually was. And in fact, it goes both ways, right? If we didn't search 0, then we won't search 3 on the next day. Okay.
Mhm.
So what that means is these sequences are the sequence for 3 can actually be obtained from the sequence of 0, right? So these are going to always be the same, and these are going to be the same. These are going to be the same, and so on. So the pattern continues. Whatever this sequence was, this the sequence for 0, the sequence for 3 is just going to be the same sequence prepended by this initial value for day 1, because there is no element to go for here, right? But if we remember our rule for we don't actually have to use the rule since the search strategies are, you can say that the strategy for 3 is the same as the strategy for 0, except we waste 1 day. Okay. So that means that the expectation, let's go here, the expected number of days to find a treasure when it's at the spot 3 is 1 larger than when it's for 0. Just because we waste 1 day and everything else is the same. Okay. we could resort to writing down all these numbers and notice that they are actually equal from that point on. But
yeah, let's go back to the example, and I just want to highlight the rows from this other example. Make
okay.
it clear.
Yeah, of course.
So what Mikhail is saying is, if you look at this column from day one, and you look at, we know that k is 3, so we jump k spots ahead, and we look from this point on, you see that these two tables are going to be identical. And so he's just rewriting the expectation of from spot 3 on day 2 as being the expectation from spot 0 on day 1. So it's just basically a way of compressing this table, as how I've been thinking about it.
Yeah.
All right, so I'll switch back to you.
Right. So this works, and it doesn't exactly matter that these are 2 or 3. It only matters that these are like k apart, right? So it's the same argument will work for 4 and 5 and 6 and 7 as well. Okay. We don't search any of these on the first day, and after that it's exactly the same as here. So yeah, we have these like relations, right, between these axes that were supposed to be expectations, so they are actually fixed numbers, but we cannot like it's hard to compute them directly, so we are kind of coming up with these like secondary information, I would say, about them, so that we can use that later to figure out what the actual values are. Okay. So now let's look at another example here. So here our pattern stops, right? Because if we go with x5, then we're supposed to match that with x8, but there is no x8, so there is no like continuation for this kind of pattern. But we still may look at some other case, right? So when we look at 5 and 0, these are also k apart, but only modulo n, right? So if we add 3 to 5, then modulo n we get 0. Right, and so since they are k apart, it still holds that the pattern for the 5 is going to occur for the 0 as well, with the shift of 1 step. Okay. However, the difference between this case and the previous case is that we actually search the spot 0 on day 1.
Right.
Okay. So now let's think about that, what that means in terms of relations. So how can we express x0 in terms of x5 based on the fact that their patterns are the same? So we still have a shift of 1 day, right? So the first day is going to be there no matter what. However, after the search, we continue to this pattern only with probability 1/2. Okay, so with probability 1/2, we proceed into this pattern of searches. That's actually the same as here. So the expected number of steps after this search is exactly x5. Okay. And with probability 1/2, we just finish at 1. So that's another kind of relation that we obtain. It's very similar, but like it's another kind because when going from 5 to 0 by adding 3 modulo 8, we have to go over the 8. Okay.
So let's, can we go back to my example?
Sure.
And see exactly where that shift occurs? Okay.
Yes.
Okay, so the values are a little different here. So they're 7 and 3. So which row is that shift occurring?
Let's go with 4 and 0.
So 4 and 0. So
Yeah.
the cave days or the so those or days?
Yes.
Okay, and then which days do you see the shift occurring for?
So on day 0, we initially have 1, right?
So our day 1.
On the first day, we have 1 on day 0, and all the subsequent numbers are the same as in column 4, except they are 2 times smaller.
Okay, so this one right here? Or
No. The columns 0 and 4.
Oh, columns 0 and 4. Okay.
Yeah, so here and here, except if we skip day 1 in the column 0.
Okay, so skip this day.
Yes, and if we match all the next numbers like with shift 1, right? So day 2 for 0 and day 1 for 4, for example.
So these two?
Okay, so let's go with day 2 for the spot 0.
Okay.
And then day 1 for the spot 4.
Okay.
Okay, so the left number is 2 times smaller than the right number. And if we move them down.
I see. So these two spots are matched. These two spots are matched.
Yeah,
and
exactly.
But to a multiplier of 1/2.
Yes, exactly.
Okay. And so now this is more clear. So and then so how would you write this out in terms of the formula? So we would say.
So the sum for 0 is just 1 because it's unmatched, right? So 1 is unmatched.
Okay.
And so all the rest of the numbers are just like a carbon copy of column 4, except 2 times smaller.
Okay, so then we'd do 1/2 the expectation on 4.
Yeah, exactly.
Okay, this makes sense to me now. All right. So should we continue here or switch back to yours?
Let's switch back.
Okay.
Right. So let me see my notes here real quick. Yeah, perfect. Okay, so we can write this down for x0. So it's going to be x5 over 2 plus 1. And the same works when these are k apart. So it's like with the looping modulo 8. Right? So it's going to be x1 is x6 plus over 2 plus 1. And x2 is x7 over 2 plus 1. Okay? So we can write down this. So this is a system of equations, basically. That so we have n variables and also n equations. And all of these are linear equations. So it's kind of natural to expect that it only suffices to look at this sequence, at this system of equations, to determine the values of x, all the values of x. And remember that the answer that we are interested in is actually the average value of all the x's. Okay, so that's what we want to compute given this table. So one way of like thinking about that, right, is, well, let me go maybe a bit lower. So we can think of it as sorry, I want a different color. So yeah, and we can see that there are two kinds of linear relations here, right? So we can call these, like here, when we don't have like this overflow modulo n, we can call these type A, and these we're going to call type B. Okay, so there's always a relation between xi and xi plus k modulo n. Okay, so here, but the type actually depends on if the overflow happens. So if I plus k is less than n, then it's going to be type A. And if I plus k is at least n, it's going to be type B. Right? So it's how, if we draw all these variables in a circle, then we would have like this relation x3 is equal to x0 plus 1, would allow us to compute x3, at least that one, in terms of x0 with relation of type A. Okay, and so we have these relations like these. So all of these are type A, except when and the pattern, like this circular pattern, continues. So we still have x0 related to x5, but since these like going forward crosses like the boundary where we cut the circle, it's of type B now. Okay. Probably not a very great picture, but we can think of this as like circular relations, right? Modulo n.
So is it, you're thinking about it in the table, like a type B versus type A relation is grabbing the value from the same table versus the previous instance of the table? Or
you mean in terms of this table here?
Well, I wanted to, is there a way to like match this to the day table, like show like a type A versus a type B on the example I drew?
Yeah, so in terms of the table that you have on your screen, x0 is just the sum of all numbers in column 0.
Mm-hmm.
And x1 is the sum of all numbers in column 1, and so on.
Oh, yeah, I see.
Mm-hmm.
I see how this ends up working, because you, yeah, let's switch back to my example, and I'll,
of course.
So and if I'm wrong, you can correct me, but here's this is type 1, right? So this is moving from x, so you're writing x3 in terms of x0, right?
Yes.
So it's plus 1. So you see we've added an extra day to type 0. And then everything else in the table from these two circles on is the same.
Yeah.
But then if we're trying to move from, where's a good wraparound case?
4 and 0, probably.
4 and 0, which day? Oh, just on these 2 days. Okay. So we have here and here. So if we were on day 4 and moving to day 0, we end up having a relation. This holds for any pair of cells with this offset. So it could even be these.
Yes.
What you can do is you can continue on And you'll notice that it ends up having this relation. So we have x0, and it's just coming from, we look at the previous value of x4, so, and then divide by 2. I think am I missing something here? Or this
Yeah,
is,
by 2 and plus 1.
and then plus 1. Okay.
Mm-hmm.
Yeah. Okay, so I see the two types of relations now a little more clearly, but I just wanted to map it back to the table we built before if people were getting lost.
Mm-hmm.
All right, let's switch back to you.
Okay. So at this point, we have this so this in fact determine the x's like unambiguously, and we can compute the answer. And so now I'm not going to actually do this, but what you can do is, for example, find a value for x0 in some way, and then use these relations to determine all the other ones. Because if we know x0, then we know x3, then we know x8, then we know x1, and so on. And the way to find out what x0 is again plug in the relations. So it's x5 over 2 plus 1 because we have this relation. But for x5, we have these. So we can plug x2. But for x2, we also have this relation, right? So we can plug x2 here and then x7 and so on. And eventually, after n steps, we're going to have like an expression back in terms of x0 because it loops around, remember? So it's going to be a x0 plus b eventually after n steps. So what we can do now is find x0 as b over, let's see, 1 minus a. And then as we have x0, then we again can plug it back into these relations and find out what all the other variables are equal to. And that's how we can find the answer, right? So now we can solve the problem in linear time because plugging this relation or relations only take like constant time each step. So the other problem that we might have, like remember how we cannot divide by 0 modulo anything. So if a is equal to 1 modulo our prime number, then it's bad for us. However, we can see that when plugging this relation, the a coefficient only decreases when we use a type b relation. Mm-hmm. And since we're going to use all of them, then a is actually 2 to the power of k, always. And the smallest value when 2 to the kth is equal to 1 modulo p is when k is p minus 1 over 2, which is 5 times 10 to the 8th plus 3. And this is
yeah, so, it's larger than the value of n. So
yeah, so n is just barely like it's very close to this border and if we actually have k equal to this value, then actually all the solution just breaks because we cannot solve this anymore. So I had to be a little careful about setting the limits here.
Yeah, and so p is 10 to the 9th plus 7, just to remind people.
Yeah.
And so, yeah. And so you can see that the bounds were chosen very, very carefully.
Mm-hmm. Yeah. And I also, I initially wanted to set n to be as large as 10 to the 9th, but I'm glad I didn't. Because that would be very embarrassing to discover. Right, so I think we're like at an hour mark now, roughly.
Yeah.
Do we maybe have any questions? Because
yeah,
we're going to a different part of the discussion.
Oh yeah. So if anyone, so what kind of questions were you looking for?
I mean, maybe something was not clear about all of that.
Yeah, so if anyone has any questions from people that are viewing, just put them in the chat and we'll be able to read them. So someone asked, when are we going to answer Q&A? So we'll do Q&A at the end after we finish the problem. So if you have questions specifically for Mikhail, then we'll answer those at the end. If you have questions about the problem, put them in the chat now and we'll clarify anything that wasn't clear. We had a question about my flow series, which will be coming back soon. I just found a lot of guests recently that wanted to do episodes, so I've been doing guest episodes. And I think they're a lot of fun. But I'll be back to that soon. There was a comment that people would have wanted to see the episode more if they had seen your handle on Codeforces rather than your name. I guess that's a fair point, but yeah, I listed it in the Codeforces blog post with the handle. I listed it both ways, so maybe it grabbed a few people. Some people didn't know your real name though. We don't have any questions yet, but I'll keep an eye on the chat and then answer them as they come up.
Okay, so maybe I'll just go on a bit about that problem. So this is the point where we kind of disregard everything about the original problem, about the treasures, chances, and everything else, and this system of equation like becomes our problem. Okay, so what we now want to do is to, well, let's. So we want to find the answer, but instead let's resort to just finding x0 for the time being. Okay. So we have these relations. Maybe if I would like to copy that. Is there any way I can copy like a portion of that?
Yeah, you can highlight it with your mouse and then right click and then you can copy and then paste it. You can also highlight select. It works as well, but I don't know.
Yeah, let's see if it's good or not.
Control C, Control V will work, I believe.
Yeah. Good enough. So it was supposed to be x3, x, like that, and then it was type A, and then it was type B. Right. So we have these relations, but now what we want to do is, yeah, let's just do that.
Actually, we got one question. So if you want to,
yeah, sure,
answer this one. The questions from David Harmeyer is, can you explain how to find A and B in the AX 0 plus B equation?
Oh, of course. So yeah, so what you have here is like you always have an equation. So it's basically composing two linear equations. So if we have a relation like that, right? So x in terms of other variable y, like here, for example. But then we have an expression of y in terms of another variable z, right? So this expression would be this, but then we want to like plug in y from another expression. So, and that would be this one. Perfect arrow. Okay. And so now we can determine. We want to determine x in terms of z. So if we plug that in, that would be A times C, that was D, plus B. And that's equal AC times Z plus AD times AD plus B, right? So this becomes a new A, and this becomes a new B. Okay, so what happens here is we start like we want to express x0 in terms of like another variable, and we want to change that variable by plugging the expressions. So, and the actual coefficients that we plug in here depend on whether it's type A or type B relation we are using. Okay, and then we just use these to decompose to linear relations. Yeah, that's probably it. Right, and in the end, our variable that we are expressing x0 in terms of becomes x0 again, right? Because the relations loop around.
Yeah, the question they were asking is, wouldn't we need to plug in the equation 5 times 10 to the 8th times to get back to x0? And I think that's true because we're O of n right now with our solution, correct?
Yeah, exactly. So that's not the like the full solution, but it gives us an idea that like first of all, these equations kind of work, and also they are enough to actually find the answer.
And so here's a question I have. Did you code this particular solution when you were testing the problem, like the intermediate solution?
Yeah, of course. I mean, it's very simple to code, and you have to check your answers anyway. So yeah, I had that solution.
And did you also code the n squared solution that you had before to verify?
Yeah, I think so. As a matter of fact, it took me a very long time to like come up with an efficient solution for that. So I was kind of like, as I explained, I was actually going through all the steps that I'm taking here.
So when you were writing the problem, you started with the n squared problem, and then you just kept going until you could find this bound?
Yeah, so the legend just came to my mind, and then I just started solving it and making observations, and it didn't work. And then I kind of like tried different ideas. So it was I was as frustrated to solve it as the contestants probably, and it took me much longer than 2 hours for Codeforces run. So yeah, that's how you set problems, I guess.
I think it took all the contestants longer than 2 hours too, right? No one solved it. Is that correct?
Yeah, no one solved that, but they had other problems as well.
Yeah.
Oh, okay. Right. So so I want to do this trick with these expressions. So I'm going to do the plugging again, but now I won't do it all the way, right? So what I'm going to do is I'm going to start with one of the first k variables, okay? So for one of the first k variables, we have a type B expression here, right? Because the left-hand sides are exactly the first k variables. Remember, n equals 4, k equals 3. Okay, so we have a type B relation. Then we go all the way here to x5. And from here, we can start to use type A expressions, right? So we use type A expression from here and get something like x2 over 2 plus 3 over 2. Okay, so what we're doing is we're using type B and then start using type A repeatedly. Well, it was only one time here, but the thing is, we want to stop once we're back again in the first k variables. Okay?
I see. So you're mapping the expected value to only the first k, so that you only have to deal with the first k and not all of n.
Yeah. For now, I'm only going for like determine any of these values, and we'll talk about how to recover the answer later.
Okay.
Okay. So here we obtain this expression, right? Just by plugging it, but not all the way, and we're back at x2 again. And what we now it may seem weird, but at this point we actually want to revert that. Okay. So we are going to express x. Let's see. Yeah, we're going to express x2 in terms of x0. It's pretty easy when you have the coefficients here. I think it's going to be 2x0 minus 3. So this may seem arbitrary, but it's like it will be easier to see the point in the end. Okay, so let's do the same thing with x1. So we start with the type B relation here. And then we start doing type A relations. So we plug these here. So again, the same result as before, but now we can make one more type A relation. Okay, so that becomes x0 over 2 plus 5 seconds. Okay, and again we like revert the relation, so it becomes x0 is equal to 2x1 minus 5. And with x2 we can do the same thing, and as a matter of fact it's going to be the same relation as here, except it's going to be x1 in terms of x2. Okay, so right, let me it's not I should have like let me put that in the same place, all these relations. No. Can you please come on. Okay, I'm going to copy that here. Yeah. Okay. Sorry. I'm bad at this. Right. Okay. And then I think it's just simpler if I write it down. So I want to put that down in the same place. Okay. So that's another system of relations, but you can see that again, it's a circular system of relations, but it only involves 3 variables except for 8, right? So it's like a simpler instance. And what you can notice further is that, again, there are 2 types of relations here. Okay, so we have these like kind of type A, and also something that resembles type B, I guess. So if that were actually type A, so that kind of corresponds to a system with n equals 3 and k equals 2, I guess, right? Because here we started from like any number, any index, so that adding k does not overflow. And here we can start from 0 and go to x2. And here again, we are adding 2 modulo 3. And these end up being different relations than this one. Okay, so kind of magically by doing this trick, we ended up with a smaller system of relations for some reason. So it's not really magic. So let's see how that works. So we started from I, where let me. we started with any index I that was like between 0 and k minus 1. So then we used type B relation. So what we did is we went to the index I plus n minus k. Okay. So here x6 is 1 plus 8 minus 3. Right? And then as we went with our type A relations, we would subtract k until our new number j is less than k. Okay, so that's we're trying to establish the relation between the indices here. So yeah, you can see that subtracting operation while until we arrive at this is actually just taking this thing modulo k, right? So if we start at the variable I, then j is actually going to be I plus n modulo k. So here we are going to relate xi with xi plus n modulo k. So that explains this looping modulo k behavior, right? And what about the type B and type A relation? What's the deal with that? So you can see that the reason why we've obtained two different relations here is here we had only one type A relation, and here we had two type B relations, type A relations, and here as well. Okay. So what ends up happening is, so the number of A's that we are doing here is exactly I plus n over k rounded down minus 1, right? Because that's the number of subtractions of k that we can use to get into this interval. So now let's talk a little bit general. So let's say that A and B are arbitrary linear transformations, right? So they are different. So what I mean by linear transformations is A of x is a function that's determined by two numbers. Well, let's say that it's, yeah, let's go with ax plus b. And b of x is another relation, which is cx plus d. So for like determining a, we only need a and b. And for determining b, we only need c and d. Okay, so let's look at this at the relation that we end up having after doing this process. So what happens is, like, we start, what is the relation that we actually obtain? So we end up having xi is equal to b of xi plus n minus k. Okay, but then as we start plugging A relations, we are we're plugging this B relation like instead of so, and this is in fact A of like x and k, right? So it's going to be B of A of something. And in the end, we're going to have B of applied to A to this power. This one applied to x I plus n modulo k. Right? And then we have to, like, we did the reverse thing, right? So we can do the reverse thing. and have that this variable is equal to, let's see, so it's going to be a to the power of minus that. It should be 1 minus I plus n over k, applied to b, the inverse of b applied to xi. Okay, so what do I mean by like raising a to the power x? It actually just means a applied to itself x times.
Mm.
And we can also talk about like negative powers, because a minus 1, a to the power of minus 1 is like, there is a unique linear transformation that's inverse to a. We can find it as x plus b. So let's say that a minus 1 is like cx plus d. So when we apply them together, we should just have x, right? So, okay. So this should just be always equal to x. So what that means is AC should be 1 and AD plus B should be 0. And what that means is C is 1 over A and D is minus B over A. So A minus 1 is this relation, and then negative powers are just powers of this thing. Yeah, so right, so, and depending on like, so there can be two different linear relations that can now show up here, depending on what this value is equal to, right? So plus n over k. It could be either equal to just n over k when I, let's see here, and I plus n mod k is less than k, right? Because there is no additional multiple of k happening here. This is the case, and then we have increased by 1 otherwise.
So this is kind of like a generalization of type A and B, or?
Well, it's just when for this range of i's we have, and we end up having one kind of this relation. I guess it's like new a's and b's. So let's look at our like so it's going to be like it's kind of our, did we have, yeah, see, it's kind of the same idea, except we now have, we had k and n here and k and n here, but now we end up having n mod k in place of k and k in place of n.
And that should look familiar if you're familiar with the Euclidean algorithm, right?
Yeah, so it kind of looks like we started with the problem with some value of n and k, and after applying this process, it looks exactly the same, except n is replaced by k and k is replaced by n mod k.
So yeah, and we know that if you take this transformation several times, the amount of time it takes to converge to a case where it's some value and then 0 is log n, right?
Yeah, so that's just, if we just had the numbers, that would be just the standard Euclids. Okay. And the number of steps the Euclid algorithm takes to converge is like logarithm in the worst case. Yeah, but we kind of have a lot more going on here, right? Because So to go forward, we have to compute new A and B. So our input to our, so we have this recursive procedure that kind of goes forward and forward. So the input is N, K, but we also have A and B. Okay, so to go forward, well, N changes to K, K changes to N mod K. So what becomes with A and B? So just applying our rule here. So this, if we plug this exponent here, that's going to be our A. So A becomes A to the power 1 minus N over K applied to inverse of B, and B becomes we have plus 1 here, so it just cancels with this one, right? Applied to inverse of B. Yeah. So we have these rules, and then it kind of, if you look at this from a very high level, so very abstract, it's kind of a Euclid's algorithm that for some reason needs to store these things as well.
I remember when you first told me about this problem, you described it as Euclidean algorithm on steroids, which I thought was funny.
Yeah, it kind of is. But yeah, it happens to be that way. So one question that one may have is, how do we actually, when n is large, so how do we actually compute these exponents? Right? So we have to obtain the coefficients for that. We kind of can't plug one into the other, but how to raise, how to apply a linear operator to itself a lot of times. So let's talk about that a little bit. So how to raise a linear operator to this power. So if A is equal to AXB. So let's say that A to the power of t, it's still going to be a linear function. So let's say that we have these parameters here. Okay, so AT and BT. So now, as we increase our power, it's going to be no. Okay, ATX plus T plus B. So that's equal A times AT x plus A BT plus B. So we can write this in terms of matrix multiplication as we go from ATBT to AT plus 1 BT plus 1 is we should take the previous vector and multiply it by matrix. Yeah, let's see here. So this is the new, yes, AT plus 1, right? So I think it goes like that, and then it goes like that. Is it? No, not really. So B here, we have to add on its own. So we had to actually introduce an additional component 1 here. Right. So the matrix should be A00. So BT is A. This value is A times this value. So B goes here, and no, it's A. I'm bad at this. Right. So it's A times BT plus, as we multiply this, also an extra B times 1. And then 1 just sits in its place and is not changed. Okay. So what that means is we are always multiplying by this matrix. So that means that if this matrix is M, then it's just M to the power of, I guess, t plus 1 times the vector with zeros here. And a to the power of 0 is an identity transformation, so it has to be this. Okay, so this is the way we can use our matrix exponentiation to compute the compositional power of linear operators, and then we just use it here, and yeah, and that's how we make our recursive step.
So here's a question. Have you seen this linear transformation trick, like applying the composite multiple times on a matrix in a problem before?
Yeah, I'm pretty sure I saw it. I can't remember the exact problem, but I feel like it's a fairly common application. There are lots of problems about matrix multiplications. It's usually applied to dynamic programming. So if you solve a lot of that, you can kind of see the similarities after that. Yeah. Right. So this is how we make the recursive step. And when do we terminate? So when we terminate, n is equal to 1 and k is equal to 0. So in Euclid's algorithm, that the result is going to be the greatest common divisor. But remember how we divided n and k by the greatest common divisor. So it's going to be 1 always. And also some a and b. So k is equal to 0. So what that means is we just have x is equal to a of x for some numbers. And then we can just solve for x. And that is actually x0, right? That's not right. A. Okay. So in fact, this linear transformation A that we obtain here is the same linear transformation we would obtain by plugging all the relations together, except we kind of did it more efficiently now. Right? So we kind of skipped, if we you can think of it like that. If we do this optimization, there are some type B's relations that happen here, like B followed by A followed by A, and so on. And what we're doing in each step is we are grouping some of these relations together, and then solve the problem for the new grouped relation, if you think of it like that. Okay, so yeah, let's talk about the complexity of that. So we have log n steps, but we also have to raise matrix to some power, and that power can be as high as n potentially. So the complexity is log squared, I think. Right, but we did not exactly solve the problem, did we? Because we only have x0 and we need the sum of all numbers. So how do we deal with that? The general idea stays the same, but now the problem is, of course, is when we are reducing from n variables to k variables, then the sum decreases, right? Naturally. So what we're now going to say that is when we reduce from a large problem to a small one, we're going to say that the elements in the new problem are responsible for some of the elements in the that we've removed. For example, we're going to say that. Let's actually get back to our example here. So when we reduce from 8 variables to only 3 of them, what we're going to say that for x0 is, okay, you are now responsible for all the variables with the same remainder modulo k. And for x0, it's the same. So each of them is responsible for actually 3 variables. Now, I'll explain what I mean by that in a minute. And x2 is only responsible for x5 as well. So what do we mean by responsible? So see, we want to compute this thing. It doesn't work out. So let's say that instead of this, we are going to compute a kind of, instead of actual values of variables, we're going to compute some kind of, the sum of some kind of linear transformations for that. So Vi is going to be, is supposed to be the sum of all variables that xi is responsible for. So for example, let's look at V0 of x0. It's supposed to be x0 plus x3 plus x6, right? But we know that x3 is a of x0, and x6 is a squared of x0. So this ends up being the sum from 0 to t, a to the power of j of x0. And we can actually group it like that. So A is a linear transformation, so this is a linear transformation as well. So now as we go to the next step with 3 variables, we know that when we are going to actually compute the answer, it's not x0 that's going to count, but rather this value.
And so Vi is basically holding like the entire equivalence class for that modulus of k.
Yeah, and as we go further, we're going to, when we're doing this step, we're going to sum the v's for these variables as well, because we're going to merge all these classes together.
Wow, this is really cool.
Yeah, so of course, like I wrote vi here because you can see that these v's can actually be different. However, you can with the same argument, you can see that it only depends on the number of these k transitions that we can fit within the array. So they can be of type A and type B as well.
Okay, so like you could have a 2 at the top of the summation, or a just a 1 on top of the summation. It's
right. Yeah, exactly.
Yeah. Okay, because it's how many times you can jump, and depending, like if it divides evenly, there's only 1 type. But if it doesn't divide evenly, then you can jump off the end, and that's when you get a segment that's a different type transformation.
Yeah, exactly. So the partition is actually going to be the same. So type A applies when I plus k is less than n, and I plus k larger than n.
Very cool.
Yeah, and so now to make this work, we just have to make additional input to our problem. Is this like VA and VB, right? 2 different types. And initially, both of these are just an identity transformation, but then they kind of compose together and such. Yeah, so in the end, when you have x0, what you just do is you plug this inside VA. And that's how you compute the answer. One final note is that you have to be able to compute these linear transformation, the sums of linear transformations, right? So instead of just a to the power of t, you have to be able to compute this sum. And you can kind of adapt the matrix exponentiation like that if you are familiar with the trick when you have to sum up your intermediate values as you go. You can just add 2 more variables and say that they are like the preliminary sum. But you can also say that it's a to the power of t minus 1, where 1 is like identity transformation, composed with, let's see, a minus 1 minus I inverse. And that's like the formula for geometrical progressions. No. So this is not the case. It resembles the formula for the geometrical progression, except instead of multiplication we have composition, and instead of division we have inverses. So, but that only works when A is not equal to identity, and when A is equal to identity, then it's just plus 1 times identity, I think. Yeah, so you can just reduce to exponentiation, computing this geometrical progression. Ooh, yeah, so I think that finally does it. You can see that there are quite a lot of steps and observations, and if you weren't quite following all of that, that's totally okay. That's totally fine. Don't worry about that at all. Yeah.
What I like about this problem, so it's a really tough problem, but the statement is very simple at the beginning, and there's all this natural structure that you progress through to get to the solution. And then the other thing I think that's kind of cool is when I was coaching, I'd give people problems like this because there's subtasks in here that can be applied to other problems. So like this linear transformation, being able to raise that to a power, I think is a really cool trick. If you haven't seen that before, now you can use it on simpler problems. Maybe you can't solve something this difficult, but there could be another problem. It's like, oh, I see linear transformation. I can apply this trick. So it's a really good learning problem, I think, even though it's like a hard competitive problem on its own. So,
yeah, even if you don't understand the full solutions, there are like, wow, that's a lot.
Yeah, a lot of steps. It's also a good time if anyone has any questions for Mikhail, we can answer those in a few seconds. So just pop those in the chat if you have a question. And yeah. So how do you, so I've noticed this trend with a lot of your previous problems is you end up having these really simple statements, but then when you read into the analysis, it's pretty complex and you have to make a lot of observations to get down to the full solution. So how does your problem solving process work to create this kind of problem?
It's really like, it can be different things. Like for this problem, I think, I don't actually remember, but it usually goes like you try to think of a legend that's interesting, and you either end up with a really trivial and well-known problem or an unsolvable problem. And what you do after that, if like it's unsolvable, you're thinking that like, okay, maybe I can make these modifications to make it simpler, and maybe it will become like interesting and can be solved efficiently. And if it's too trivial, then you think, okay, maybe I can make this harder. Or if you think that it's like well within the boundaries of what everyone knows and it's very boring, you might think about how can I make this different in a way, like apply it to like a different object or make a complication, or I don't know. Sometimes you just start to mock the problem and try to apply it in, like, ask the completely opposite question and stuff like that. Introduce randomness to make everything. So these are just really good techniques for creating interesting problems. And as for, yeah, I really like the problems that look really simple on the outside, but have a lot like inside of them. So you have to work through a lot of stuff. And like the fact that I end up with these problems is just, I don't stop until I think the problem is good. And it may be like, it takes a really, really long time to come up with a very good problem. Like sometimes an idea just pops in your head, and but it happens very rarely. What I usually end up like thinking for a few days, making alterations and stuff until I think that the problem is good enough.
Yeah, this is actually, it's interesting because your process is kind of similar to mine when I write problems.
Yeah.
Because I pretty much think the same way. I start with, sometimes I'll read like math puzzle books and I will ignore the trick for the math puzzle. I'll just think about what structure it is or something like this and keep modifying it until I have something I can solve or can't solve. But I usually have a step where after all those modifications, the problem became really complex. But then there's like a really cool trick somewhere in there. So I have to like trim away all the stuff that doesn't matter.
Yeah, sometimes you also want to build around the trick, right? Around an idea. And what I also recommend, not for problem setting, but for like, I guess, practice in general and learning, is when you learn a new trick, like for example, you learned about like the linear transformation exponentiation, right? So to understand things better, it's useful to think, okay, so I have this technique, how can I apply it in different settings and try to come up with a problem that uses this trick, because you will think about it like from different angles and you will understand it better after that. So I think that's useful.
How would you think that problem writing has affected your problem solving abilities?
I think it was useful. So what I've noticed is there are almost none like red participants who do not think about their original problems. So there may be something, there may be a connection, because it's really effective when you're problem setting. You're always thinking about different kinds of stuff that probably no one ever thought before, and you're understanding things in great detail. So yeah, do problem setting if you want to become better.
Yeah, so I had another question I think is interesting. Do you have any advice for people trying to coach teams for ICPC?
Oh, okay. So coaching can be very different in terms of like where do you come from, right? Because for some universities, they are lucky to have a lot of talented students that come and like interested in ICPC from the start. But there are some universities, of course, that ICPC is not big, and maybe like the students are like I don't know. It's not the first priority. So the best students go to other universities, and in all these cases, you kind of have to face very different challenges, right? Because when you have like beginner students that are, for example, First of all, you have to like make students interested, right? So you have to make some activity, like make some announcements and arrangements for trainings and stuff. But the students are kind of, it's probably maybe in some respect easier to teach them if you're somewhat experienced, because you just have to explain basic algorithms and stuff. And if you have really, really talented students, it may be hard to keep up with them. And, you know, they may start to think that they're like, they're better than you, and so there's no way you can help them and stuff. So, yeah, I guess.
Yeah, I think that's similar to some of my experience. Eventually, I think it becomes more like guiding what they should focus on learning next, as opposed to like, I think early in a career, you can teach them a lot of really basic stuff because it's natural to you. You've seen it a lot. But then when you start getting, they'll pretty much know everything you know after a few years. And then I think you kind of transition to, you should go read about this thing I don't know how to do. Is how I've started to guide students that are more advanced than me. But
yeah, so another thing about coaching is like, when I started coaching, I the students were like maybe roughly my age, maybe a bit younger. So I couldn't teach them anything per se. So I think that one of my goals at that point, and like I think it's important point for any kind of coach, is to try to build a community of students within your university, because when there is no coaching, people can feel kind of isolated. And I had that when I was studying at like Moscow State, because we barely had any coaching, and you felt just abandoned, and you didn't want to train a lot. But when you have this community, it really drives people to like communicate and train and compete with each other and stuff. So if anything, if you're like not a competitive programmer person at all, at the very least, you can try to like engage students and stuff, and that's really helpful.
Yeah, I definitely agree with that. And one thing I think is kind of nice, if you can build that community, is the older students start to train the younger students.
Yeah, that happens. That's really nice.
Yeah, and I think if there's something you can learn if you're more advanced, that's something that can make you a lot better, I think. If you're explaining some of these concepts to younger students, you'll develop more of a mastery of the basic concepts. So being able to either teach students that want to learn from you, or writing your own problems, these are all things, I think that's how you get to red on Codeforces. I don't know, I haven't ever hit that stage, but
yeah, I don't know.
It's fun to, I think the other thing about writing hard problems that's a lot of fun is you can see how maybe you can't solve a problem at that level in contest time, but you can go through the same thinking process and solve it the same way an advanced competitor would, but they'll take way less time, which is interesting.
Yeah.
Cool. Let's see if there's any more questions. It looks like there's not as many questions, but I think some of it just had to do with not as many people knowing your real name.
Okay.
Yeah. Well, maybe we can have you back on in a future episode, and
yeah, of course.
And label it the other way and see how many more people attend. I think it's also middle of the week versus the weekend. I think some students if they have classes or job or anything, they'll. So you may get lots of questions in the comments of this video after.
Oh, okay. Yeah. I like as you probably know, I have this channel where I usually just post my screencasts, and so I hope to have some more content there soon, like maybe some discussions of some of my other problems or like just general banter and stuff. So yeah.
Can you write down a link to the channel so that people can find it? I think it's just YouTube and then / your Codeforces handle. Maybe that's not right.
Sorry?
I was wondering if you could give a link to the viewers that are interested.
Okay, are you on my screen now?
Yeah, I'm on your screen. Yeah.
Well, you can just search for my name on YouTube. I'm not really comfortable speaking back to my environment right now. Maybe we can put like the link in the comments.
I can write it actually. I have the link right here, and so if you go to youtube.com/user/ and so you currently have screencasts on there, but then you'll start putting more educational content up.
Yeah, I was going to make a Q&A video. Like I had a thread on Codeforces because people like ask me stuff all the time in the messages. So I received a bunch of interesting questions. So hopefully I'll make this happen in a few days. And then yeah, I'd really love to discuss some of the problems, mine or otherwise, or maybe just like answer people's questions if that's what they're interested in. So we will see how it goes.
Yeah, well, I'm definitely very interested in seeing what you post in the coming days, and I'm hoping more people will go follow this after this video and can see the answers to these questions. All right, so thank you for coming on Algorithms Live, and yeah, I hope you can come back sometime. That would be really cool.
Thank you, Matt. It was really fun, and it's a great channel. Everyone should follow that. Totally, yeah. That's
thank
great.
You. Great. Bye, everyone.
All right. Bye-bye.